All right, all you calculus kiddos out there. Um, we are going to be starting assignment 4B today. Again, it's rates of change. Now, I did a couple tricks in the last video. I don't know if you really mentioned it. I think it was more to just keep my brain straight. But I did some tricks. And let me kind of define a derivative. Okay, a derivative pretty much from here on, like from the beginning was d over dx, and for some reason, this always just meant, hey, we're taking the derivative of something right here. Okay, we're just taking a derivative of it. Okay, which is true. Yes, that is true. But what do these letters mean? What does that mean? Like, without any context, that really doesn't mean anything. Or you'll see a derivative as dy dx or something like that. That's also a derivative. Okay. Think of the letter D as the words like change in. So this would be a change in y over the change in x. A change in y over the change in x. Okay, so a change in y, this is a Greek letter delta, over a change in x. A change in y over a change in x. That is, in essence, a slope. Okay, that is a slope. It's a change in y over change in x. So think of the letter D as being the word change in. All right? Now, sometimes, what if I said d dx, or let's see, dy dx, when y is equal to a b squared c to the third, actually here, I'll do it like this, e to the fourth. All right, what would be the derivative of that? And unless a, b, c, or d is some mysterious equation that has an x in it, that's equal to 0. All right? So this is a change in y with the change in x. So what this is saying is this has to be the letter that you're taking the derivative of. And so we're not quite to the point of what is called implicit differentiation. But what I want you to know right now is this is the letter that you're focusing on. But it is totally legal, if necessary, to change that letter. So what would be dy dA? What would dy dA? Well, you're taking the derivative of this y with respect to a. So dy dA would be focusing on this a. And so the a is, think of it like kind of like the letter x. So that goes away, and that leaves b squared, c to the third, d to the fourth. What would dy dB be? Dy dB. So focus on the b from the original, and that'd be 2. A, b to the first power, c to the third, d to the fourth. All right, and I know this is kind of a large leap, but what I'm really trying to teach you is D is the word change in, and then this is the letter that you need to have your equation written in. It makes it really, really difficult if that bottom letter isn't what it's supposed to be. Not saying that it's impossible, but again, we're not to the point of implicit differentiation. Okay. So the length of a rectangle, I'll just draw a rectangle here, pictures, is 6t plus 5. Its height is square root t, or t to the 1/2. Where t is time in seconds and the dimensions are in centimeters. All right. Find the rate of change in the area with respect to time. All right. So area of a rectangle is length times height, apparently, in this situation. L times H, length times height. All right? So they want me to find what is the rate of change in the area with respect to time. So change in area over change in time. Now, as I just got done saying on this other slide, wherever it went, it is damn near impossible to take the derivative of something if the equation itself isn't written with that letter. So for instance, I don't see any t's. I don't see any t's. I can find the change in area with respect to time by taking dA dt, aka the derivative, but I don't have any t's to work with right now. So my mission in life right now is to first not change anything, but rewrite this formula. And so the length is 6t plus 5, and the height is square root t. Now that the equation is written with t's, now taking this with respect to t makes a lot more sense. Way easier now. And so this is u times v, so u prime is 6 plus, leave the first bit alone, derivative of the second. I don't have to clean it up because no, I do have to clean it up. So the change in area over change in time, this is 6 square root t plus 6t plus 5 over 2 square root t. This side needs a 2 square root t. And so this is going to be what, 12t, 12t plus 6t plus 5 over 2t, so 2 square root t. Which is equal to 18t plus 5 over 2 square root t. That's the change in area with the change in time. And the label on this is just what this derivative is representing. So area is, in this case, is what, centimeters squared, that's an area, over time, and I believe this was in seconds or something like that. So this would be, its end-all be-all label would be centimeters squared over seconds. Population of 500 bacteria is introduced into a culture that grows in number according to the equation. All right, so that's the position, that's the population, where t is measured in hours. Find the rate of the population. So the rate of the population, derivative of the population, when t is equal to 2. So the rate is a derivative. It's like the velocity of population. So you take the derivative of this. Okay. Thinking of this just real quick. All I need to do is take the derivative of this inside. I don't need to take the derivative of 500. It doesn't make sense. So, okay, this is the rate. And so this is d, yeah, that, which is the same thing as the derivative. I have like 1,000 different thoughts going in my head at once here, and I just need to kind of cut the chaos here just a touch. think this is just, it's a touch more easy to understand. All right, bottoms up. Derivative of the top minus, leave the top alone. Derivative of the bottom, all over the bottom squared. Okay. Because they instantaneously asked me a question, they're not, the answer isn't going to be an equation. So because the answer doesn't require an equation, I'm not going to bother actually cleaning this equation up. I could, but for what purpose? Because they want to know what is this rate of change when time is equal to 2. So I'm just going to straight up throw in a 2, even when this equation looks nasty ugly. And so here's how I'm going to do this. I'm going to teach you a trick. I'm going to do this equation, and I want t equal to 2. So I'm going to use my calculator. I'm going to take 2, and I'm going to store this, STO, stow. I'll come up with a little arrow. Again, that was this button right next to the 1, stow. And I'm going to say the letter X. Again, I use this. And so by doing that, you can store numbers into letters. So whenever I use the letter X, the calculator recognizes it as the number 2. Now you can store on top of that, let's say you wanted it to be 8, and you can store that. Now it recognizes it as 8. All right, but I want it as 2. And what the calculator does is it does math. So if I have like 3x, that's 3 times x, that's 3 times 2, that's 6. All right, so with this, all I have to do is type in essence, a good portion of this problem. All right, and again, slow down. Don't try to do all of it at once, because that's a great way to mess stuff up. So top answer is 92,000. Bottom answer is 50 plus t squared 50 plus t squared squared. Okay, so this is ultimately 92,000 divided by 2,916. Uh, 31.5501, and this is a change in population, so that's bacteria. Over time. No, I don't think it's that. So hours or something. Just make that up. Yeah, hours. It does say hours. Yeah. Wow. All right, so the velocity of an object, okay, so that's the velocity, find the velocity and the acceleration of the object when t is equal to 3. So the velocity when t is equal to 3 is just v of 3. And so that's 36 minus 3 squared. So again, I can store this in my calculator. That's 36 minus x squared. That's 27. Meters per second. And then the acceleration is the derivative of velocity, so that's going to be negative 2t, going back to the original equation. And so what is the acceleration at 3 seconds? Well, it's negative 2, so that's negative 6 meters per second squared. velocity. There's your acceleration at 3 seconds. Okay, last bit that you need to know. If velocity and acceleration at a particular time have the same sign, as in velocity is positive and acceleration is positive, or negative and negative, both of them are the exact same thing, that means the object is speeding up. Okay, and some of you might be thinking, it's like, what does that mean? If acceleration is negative, and okay, velocity and acceleration have direction associated with it. So if a velocity has a positive velocity, that means it's going right or it's going up, in essence. That's what it means to have a positive velocity. If it's going left or down, it's a negative velocity. Now, it doesn't mean that it's slowing down or anything like that. It just means it's going that direction. So if a runner is hauling ass and has a velocity that is equal to something somewhat 15 meters per second or something like that. If a runner is running 15 meters per second, that's pretty fast. What if I said that they're running negative 15 meters per second? Well, that's still running very fast. It's just they're running that direction. It doesn't really matter. All right. So that's kind of like an idea of velocity. Now, acceleration is the same idea. It's directional oriented. All right. And so think of acceleration kind of like a force. What is the force working on it? So say, for instance, an object is, I throw a ball upwards. Okay, as it's moving upwards, its velocity is going to be positive. Okay, its velocity is going to be positive. All right. What forces are being acted on that ball that is being thrown upwards? Well, obviously gravity. In which direction does gravity work? Oh, gravity is like a force that is pulling it downwards. So the acceleration is in a downwards direction, a negative direction. So what ultimately is occurring, what is happening to this ball as it's being thrown upwards? Is it speeding up or is it slowing down? Well, it's slowing down, of course, because the two things aren't working together. The ball is slowing down as it's moving upwards. The velocity is positive and the acceleration is negative. They work against each other. So it's slowing down. Okay, now let's take that ball and let's drop it. Okay, let's drop it from a height. It's moving downwards. That means its velocity is negative. What forces are occurring on that ball? Well, again, gravity is occurring on that ball, and gravity is downwards. So the acceleration is like a force, and that also is going downwards. So what ultimately is happening to this ball? That ball is speeding up. It's going faster and faster and faster downward. All right, so bottom line is if velocity and acceleration have the same signs, then it is speeding up. If they have opposite signs, then it's slowing down. Okay, velocity is that where v is measured in feet per second. Find the acceleration at all of those. All right, so v of t is 2t plus 15 underneath 100t. All right, so the acceleration is 2t plus 15 times 100 minus 100t times 2, all divided by 2t plus 15 squared. So find the acceleration at 5 seconds. I'll worry about labels here in just a second. At 10 seconds. And at 20 seconds. So this is phi per second squared. Ta-da. Yeah, that's it. All right. So highlighting what we learned today is the letter D stands for a changing. If you want a rate of something, that is a derivative. So that's a rate of something. What else did we learn? We learned speeding up and slowing down. If they have the same signs, they're speeding up. If they're opposite signs, it's slowing down. Oh shoot! So we're supposed to find the velocity and accelerator. Okay. So for instance, at time is equal to 3, right here. I don't think it's. So we didn't really come to a conclusion right here. So you notice that the velocity is positive 27 meters per second squared, yet the acceleration is negative 6 meters. So what can you say about this this object? This object is slowing down. That's the quote-unquote speed. So speed has no direction, velocity has direction. Speed has no direction, velocity has direction.